Hello everybody. Today I am going to go over the department review, which is modified for spring 2024, and this is for Utah Valley University's 1015 course, though a lot of the principles covered in this are also applicable for the 1010 course, and it's a good review for some of the college algebra that we go over. So there are, I believe, 56 questions. Let me double check. And I plan on timestamping each of the questions. So if you have this review at home, you should be able to go into either the description and the comments, both, and you should be able to see if you have like specific questions about one of them. I have them timestamped below. I also have a link to the download of this document, and yeah, so if you want to follow along, that's good. If you have it and you want to do it first and then come check your answer, that's good too. If you're struggling with a specific topic, that's fine too. The way that this is structured is that it will not, it's not all like neatly organized. So it jumps around from some of the different units that we have covered in this class. And so it's kind of tricky to say, oh, well, I'll watch the beginning and we'll be covering this thing. No, they're all pretty interspersed. So that is why I have it timestamped. But yeah, let's just get into it. Number 1 says, identify each graph below as exponential, linear, logarithmic, or quadratic. So linear is pretty self-explanatory. It's just a line. So A is going to be linear. B is quadratic. Quadratics are typically x squared. There's an x squared in there. So B is quadratic. C is going to be exponential. And D is going to be logarithmic. It's important to know the parent graph for each of the graphs that we are going to be working with in this class, especially because it is super helpful for graphing transformations. So, one moment. Okay, so here I have a graph, just a blank graph, and I'm going to demonstrate some of the parent graphs that we will be seeing because it's useful for later stuff. So the parent graph of a linear graph is f of x is equal to y. No, sorry. F of x is equal to x, which is the same as saying y equals x. And that is where you start at 1, you go up 1 over 1, up 1 over 1, down 1 over 1, blah, 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 like this. And it will end up looking something like this. The next graph. And if, when in doubt, with any graph that we do, it's really nice to have an XY chart. Sometimes, if you're dealing with a logarithmic graph, it's probably smarter to do an XY chart of its parent function and then apply the transformations to the points. Because sometimes the points that you pick can give you really bizarre results. But on like some of those graphs, it's just good to graph the parent graph first. So if you have x equals -1, your y also equals -1, 0, 0, 1, 1. It's good to have like 3 points, give or take, to get an idea of what's going on. Another form for our linear functions, and I'm going to put this under the things to know, is our y equals mx plus b. This is the standard form of a linear function. The m stands for slope. The b stands for the y-intercept. Sometimes it's referred to as the initial point. Linear functions, while the transformations that we've learned throughout the semester do apply to linear functions, it actually isn't always going to be the most useful to think of it to think of it in context of the other transformations that we have learned. It's good to just know this for linear functions. But for the other functions that we deal with, typically, so for example, let's look at quadratics. Quadratics are y equals x squared, but their parent, their vertex form goes like this: a x minus h squared plus k. Where a tends to be our shifts. A tends to be our stretches and compresses. H usually is our side-to-side movement, so if you're moving to the left or right. And K is our up and down movement. So, for example, If I had something like y is equal to 3x minus 4 squared plus 2, because of this plus 2, I know that we're going up 2. Because of this minus 4, I know we're going right 4. Now, this sometimes confuses people. When things are next to the x's in either parentheses or implied parentheses, so if it's on the bottom, like x plus 4 of something like this, or if it's in an exponent, like 3x minus 3, if there's something like that, that means it's going to be affecting our side-to-side movement or stretching or compressing. Now, in this class, we don't typically deal with side-to-side stretches and compresses. We usually only deal with up and down ones. And we also usually don't deal with side-to-side reflections. It's still good to know that typically if it's next to the x in our parentheses or implied parentheses, that it's affecting our side-to-side. And it's also usually affecting it in the way that we wouldn't expect it to. Whereas if it's outside, then it's affecting it the way that we would think. So if you have just a plus 2, then it's going up 2. If we have a times 3, then it's being stretched by 3. If we have a times 1/3, then it's being compressed by 3. Or timesed by 1/3. It's all the same. It's just how they prefer to say it. So having that in mind, a lot of the transformations in this class follow the same pattern of if you have something with implied or direct explicit parentheses and it's by the x, that's what's affecting the side-to-side movement, and it's opposite. I think I just said that all. But all of the functions typically follow the same kind of idea. Whether it be logarithmic, exponential, So coming back over here, we have the parent graph of our linear function. But let's look at the parent graph of our quadratic function. If we have our little xy chart, if we do -1, -1 squared is +1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. You'll notice that when we are doing this, quadratic functions are symmetrical. Let me just graph this real quick. And we don't have a 9 on this graph, but it would look something like this. And quadratics end up having this little U shape. So this is useful to know because with our shifts, coming back over to here, where we know, that with this is just moving our parent graph, the one that we just graphed, to the left, or it's stretching it, or it's moving it up and down. The parent graph, and it's good to know the parent graph for these graphs. The parent graph for a exponential function is going to be, usually we just start with 2 as the base to demonstrate, but it can be any number. We always start at 0, 1, like this. We always get super duper close to 0, and we go up pretty quick, like this. Hold on. It should be like this. Bloom. Yeah. So the pattern of an exponential, let's just call this B for now, is your -1 is the same as 1 over your base for your y. See how we had -1 is 1/2 when we graphed 2 to the x power. Our 0 is always 1 because something to the 0th power is 1. And then our 1 is typically our base. This is important to know. And logarithmic functions are exactly the same, but their x and y's are swapped. So what they end up looking like is something like this. Well, we'll keep this here because we know that when we are swapping, when we're doing the inverse function, we're just swapping the x and the y's. So this would come here, this would come here, this would come here, and it would get super close to 0, but it would never cross. Same in this case. These are, in our exponential functions, this is called our horizontal asymptote, and with our parent graph of an exponential function, the horizontal asymptote is always going to be y equals 0, but because with logarithms, because it's a inverse function, we just swap our x and y's. So the asymptote for a logarithmic function is x equals 0. keep in mind that when you have a logarithm, we are not allowed to have a 0 in here, and we're not allowed to have anything smaller than 0 either. So no negative numbers and no zeros. That can lead you to extraneous solutions. And that's because the reason why that is because something to an exponent, nothing that this exponent would be would ever give you a negative number if your base is positive. If it's negative, there are a few other things that go on, but it's just like a reflection about the x-axis. And then we also talked a little bit about rational functions. We did, but first I'm going to talk about square roots functions, radicals, we'll just call, and these are the inverse of quadratic functions. However, we do have restrictions. So the square root of 0, we can't have any negative number in here when it's a 2, 4, 6, or whatever in our index spot. So 0, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. So we'll do something like this, our thing. But the reason why we have some restrictions going on is because if we had the bottom, if we know that quadratic functions look like this, and we're reflecting across the x equals y, the y equals x. We can't have this because it would not count as a function because it doesn't pass the vertical line test. We can't have two different y's for one single x. So they give a restriction and cut off the bottom edge. But yeah, this is the parent graph of your radical function, which in this case is the square root. And then finally we have our rational functions, which would be 1 over x. And the parent function for this is -1 would be -1, 0. We are not allowed to have 0. That's not allowed. But 1 and 1. So we actually, with our rational functions, we end up looking something like, sorry, give me just one moment. We end up looking something like this, where it gets super duper close to our lines, but it never crosses. Occasionally, with a rational function, you'll have something like, let me clear this graph real quick. You'll have something that looks like this. I don't know if we covered that too often. I don't think we did. I don't think we covered that too much in this class. You might be asked to find the domain of something that looks like this, which isn't too tricky. You would just go up to the vertical asymptotes. But in 1050, the next math course from here, you'll be covering rational functions a little bit more and learn how to graph them. So anyway, yes, this is our parent graph of a rational function. Having that out of the way, it's good to come back up here, and we already identified, I believe, which were which. But it was good to go over. The parent graphs. So now we are on number 2, and it's asking us to solve the system of equations. Give me just 1 second to lay out a little white block so that I can have somewhere to work on. And we have this system of equations. 2x minus y equals 5, and 3x minus y equals 0. Now there's 3 ways to solve systems of equations. I would not recommend solving by graphing because you have to be extremely precise with your graphing skills, and it's kind of tricky to do that. But there are 2 different ways that we recommend. One of them is called substitution. And that's when we get one of our variables by themselves. I'm going to get my y variable by itself on this bottom equation. You could do any variable that you see, any one that you like. But I choose this one because I don't have to divide by a negative, and I don't have to, like, it's just a little bit more simpler to do it this way, but it doesn't matter. It's not like there's a right way to do it. So I'm going to do y is equal to -3x. I just minus 3x from both sides. And then we're going to take that -3x and plug it into the y above. So we get 2x minus -3x equals 5. This will turn into 2x plus 3x, which is 5x equals 5. We'll divide both sides. Let me get rid of this. We'll divide both sides by 5, and we'll get x is equal to 1. Now we need to take that x is equal to 1 and plug it into one of our equations above. I usually plug it into the equation that I did not modify. So the 2x minus y equals 5. But we found x equals 1, so we'll just be 2 times 1, which gives me 2 minus y equals 5, which gives me negative y is equal to 3, which gives me y is equal to negative 3. And so the answer for number 2 is, it will be, 1 comma 2. It wants it as a, 1 comma negative 3. I don't know where the 2 came from. It wants it as a coordinate point. Yeah. Here, let me make a little trash layer that I can put all my unused stuff. Now, let's move on to number 3. Determine if the polynomial graphed below has a positive or negative leading coefficient. Assume there are no other turning points not seen. Does the polynomial have an even or an odd degree? Let's come down here real quick and talk about some of the things that you should know. I have this handy dandy nifty little chart here. Let me just draw this out real quick. Where, I gave myself a few too many boxes. Hold on. Where if a function is even and positive, then both of the ends are going up, like a smiley face. And I usually draw a little gap in between, because sometimes you'll get crazy ones that have some like weirdness in the middle. And if it's even and it's negative, then both of the ends will be pointing downwards. If it's odd and positive, then it's kind of like a linear function where one end is starting at the bottom and the other end is ending at the top. And the other is the opposite, where one end is starting at the top and ending at the bottom. This chart is going to be handy for us up here because we can see that both of our ends are pointing downwards, which is what this chart said over here. Both of our ends are pointing downwards, which means it's even and has a negative leading coefficient. So we'll say even degree negative leading coefficient. Let's move on to number 4. Oops, it's on a new page. Number 4 asks us to determine the x-intercepts of the polynomial function graphed below. This is super simple. We have one here, we have one here, and we have one here, and they typically want them in point format. So we have a negative 3, 0. We also have a 0, 0, and we also have a 2, 0. That's your answer for number 4. Pretty simple, pretty straightforward. It's just wherever it's hitting our x-axis. 5 is asking us if f of x equals 2x minus 3 and g of x equals x to the 4th power minus 3x plus 2, find f plus g of x, f minus g of x, and f times g of x. Let me make a new little canvas for us to work on. For the first one, we will have 2 of x minus 3 plus x to the 4th minus 3x plus 2. Now, you don't necessarily need parentheses in this place, but I think it is useful when it comes to negative, when we're minusing functions. It just helps me keep the negative straight and know that it has to distribute. In this case, because we're adding, we actually don't need them, but it's a good habit to put them there. So now we will just combine like terms. So I see a 2 of x and a 3x. I also see a x to the 4th, and I see a constant and a constant. So we can add these all together, and I will get x to the 4th. Well, we can only add like terms together. So I get x to the 4th. We usually do the biggest powers first, and then minus x, and then minus 1. So that would be our answer for the first part, which is f of, f plus g of x is equal to x to the 4th. We can't really do anything else past this point. Now we should do minus, so we'll do 2 of x minus 2x minus 3 minus x 4th to the 4th power minus 3x plus 2. Now we distribute the negative. So we get 2 of x minus 3 minus x to the 4th power plus 3x minus 2. And we will do like terms again. So we will end up with f minus g of x is equal to negative x to the 4th power and then it would be plus 5x, and then it would be minus 5. And then for the last one, f times g, let me cut this and put it here so I don't delete it when I get rid of my work. So we'll have 2x minus 3. And I'm gonna clear my work above because I'm gonna need all the space I can get. So 2x minus 3 times x to the 4th minus 3x plus 2. We're gonna FOIL these out. So 2x times x to the 4th is 2x to the 5th. 2x times negative 3x is negative 6x squared. 2x times 2 is 4x. Negative 3 times x to the 4th is negative 3x to the 4th. Negative 3 times negative 3x is positive 9x. And negative 3 times positive 2 is negative 6. Now we're going to underline all our like terms. And I'm starting to feel like maybe we won't have too many. But that's okay. Okay, so our biggest one is 2x to the 5th. Here, hold on. So we have 2x to the 5th power minus, and then we have a 3x to the 4th, and then we have a minus 6x squared, and then we can add our x's, so we'll have plus 13x, and then we will have a minus 6. He's a lonely little constant, no other constants. And I'm just going to move him over so there's a little bit more room. Okay, so that was 5. 6 is pretty similar, except for it's asking us to do function composition. So we're just going to take 2x squared minus 3. And, well, we're going to take 5 minus x because it's g. G is going into f because it's after. So we're going to take f, and we're going to replace the x in f with our g. So 5 minus x squared minus 3. And now we are going to simplify. So this needs to be expanded and FOILed out. So 2 times 5 minus x times 5 minus x minus 3. And then we'll FOIL, which will give us 2 times 25 minus 10x plus x squared minus 3. 2 times all that would give me 50 minus 20x plus 2x squared minus 3. Now I'll combine my like terms. So I'll get hold on. Sorry, one sec. I'll get 2x squared minus 20x plus 47. Now, at this point, it might be useful for us to see if this is factorable. Give me just a moment. Well, it probably doesn't matter. It's not telling us to simplify per se. I would just give this. It's not asking us to like solve for 0 or anything like this. So we can say f fog. Let me get rid of this so there's more room. Oops. There's a very, very subtle difference between function composition and the multiplication. The fog has an open circle. Anyway, so our f of g of x would be equal to 2x squared minus 20x plus 47. Next is number 7, and it's asking, it's asking us to find the vertex of the parabola that represents the function f of x equals 2 times x plus 3 squared minus 4. So when we are dealing with vertex, our vertex form is a times x minus h squared plus k, and the vertex is h comma k. Notice that it's not negative h. We just take the number, we kind of take the opposite of what we're seeing. So with this, our vertex is going to be negative 3 comma negative 4 because the inside gets switched kind of. So that sometimes confuses people, but it's okay. So our answer for this is -3 comma -4. For number 8, it's asking us to evaluate g of 5 using the function g of x equals log base 3 2x minus 7. So this means we're plugging in 5 for x. So log base 3 2 times 5 minus 7. 2 times 5 is 10. So we'll get log base 3 10 minus 7. 10 minus 7 is 3, so we get log base 3 of 3. Now, one of our log properties means that if you have a log that is a base, and you got an inside that's a 3 by himself, or that has an exponent, we can't have like 3 plus 4 or whatever on the inside. It has to be by himself. That can erase into 1. And if you don't remember that rule, it's also fine to convert this into exponential form. Let's add this to things that we need to know. Log base b to a equals x. This is the same as writing base x equals a. And this is really useful. If you don't have this down, you need to have this down. Coming back here, though, we can rewrite this as log is 3 to the something equals 3, and that's just 1. So g of 5 is equal to 1. Hold on. Yep, simple as that. Number 9 is asking us to find the linear function in slope-intercept form whose graph has a slope of m equals 4 and a y-intercept of 0, 3. Now, if we come back down here, we'll remember that slope-intercept form is y equals mx plus b. The slope is our m, and the b is our y-intercept. So coming back up here to 9, we are already given m, which is super nice. So it would be y is equal to 4x plus 3. It's kind of giving us our y-intercept already. Our y-intercept is when x equals 0. If it was giving something different, you would do something different. And there will be an example later on where we will be doing something different. But for now, it's just y equals x plus 3. 4x plus 3. 10 is asking us to determine the linear function in slope-intercept form whose graph is perpendicular to g of 2x minus 7 and passes through the point 0, 3. The key word here is perpendicular. So our function, our original function, its slope is 2, and that's the same as writing as 2 over 1. Parallel functions mean that they have the same slope. However, when it's perpendicular, that means we have the slopes reciprocal, which means we flip it on its top, but we also change its sign. So if it started out negative, it turns positive. If it started out positive, it turns negative. So our new slope is -1/2. But it's not asking just for the slope. It's asking for the equation itself. And it's kind of being nice to us because it's already telling us that our y-intercept is 3. So our new equation is going to be y is equal to -1/2 x plus 3. Number 11 is asking us is telling us, using f of x equals 3 of x as the parent function, graph the transformed function f of x equals 3 to the x minus 2. Let's go down to our graph really quick. I'm going to just get rid of this. Whoops. So we had f of x is equal to x to the 3 to the x minus 2. Yeah. The parent graph of this function would be f of x to the equals 3 to the x power. And this one, let me change its color really quick so we can know the difference. The parent function here, we always start at 0, 1, like this. And then we'll go up, we'll go over 1 up our base, and then we'll go over to the left one, down 1 over our base. So that's about 1/3. So our function would look something like, our parent function would look something like this. Give or take. Now, I'm not the greatest at drawing these lines, but we'll have to make do. However, with this function, we have a -2 in our exponent. Now, if you recall, when it's by the x, either in parentheses or implied parentheses like an exponent gives, that's the same as saying we're moving to the side, and it's also the opposite of what you expect. So because it's -2, we're going to the right by 2. So our new graph looks something like this instead. That is our new graph. And that would be the answer for our problem, this darker brown graph. Let's go back up to our next problem. We just did 11, and now we are looking at 12, which says determine the inverse function of f of x equals 5x, 5 to the power of x. To do this, so when you hear the word inverse, that just means we're swapping our x and y's. That could mean we're swapping our domain and ranges. That could mean whatever. As long as we're swapping our x and y's. It also means that we're reflecting over y equals x. But that's not relevant to this problem as much. We need to change our f into y. So we'll change this into y is equal to 5 of x first. And then we'll swap our x and y's. We'll replace all of our x's with y's, and we'll replace all of our y's with x's. So we'll get x is equal to 5 to the power of y. Now, we are at a point where we need to change to logarithmic form to get the y by itself. Now, coming back down here, we remember this log conversion formula, which is log base b argument equals x is the same as b to the power of x equals the argument or answer. So we'll come back up here. Whoops, I'm too zoomed in. And we will say our log to the base 5 with the ex inside is equal to y. This would be the inverse function, though it might want you to write it as f to the power of -1 of x is equal to 5, is equal to log base 5 to the x. That would be your answer. An alternate way of doing this, if you don't remember the conversion, is you can just do log base 5 to both sides. And you would get log base 5x equals, these would cross out, giving you y, leaving you with y. That's also valid. Yeah, so let me move this down. Oh, that was not right. Whoops. So the inverse of our function would be f of -1 of x is equal to log base 5 to the x power, like this instead. 13 is asking us to graph the function f of x equals log base 2 x minus 1 plus 2, and then graph the inverse on the same system. So let's go down here. 2 x minus 1 plus 2. Okay, log. And then I feel scared sometimes that I write it down wrong. Yeah, okay, there we go. And also it's inverse. So for this one, we are going to, it might be useful for us to graph its parent first. So we always start here, unless there's an up or down transformation. Well, for a parent graph, we always start here. Then we go up 1 and then over to our base, in which case it's 2. Then we'll go left 1 to 1 over our base. So this is our parent graph of our log base 2. But because he's moving up 2, so 1, 2, and he's also moving right by 1 because it's minus and it kind of does what we at least expect it to. This is our new function. For the inverse, either you could find the inverse mathematically, but it might be easier to just give the points that you see. So we have 1.5, comma 1. We have 2, 2. And we also have 3, 3. We just swap the x and y's. So 3, 3 stays 3, 3. 2, 2 also stays 2, 2 because the 2's are swapping. But this would turn into 1, 1.5 instead. So we go to 1 and then 1.5. And we go to 2, 2. And, that's 2, 2 and then 3, 3. And our new guy would look something like this. It might be useful to know that because we have an asymptote of 1 on our original logarithmic function of of x equals 1, we'll have one of y equals 1. So it will never cross 1 with our exponential function. And that would be the answer for 13. Whoops. Hold on. Let me throw these in the trash. And move this down. And we see 14 is asking us to determine the points of intersection of f of x and g of x. Hello? Oh, 14 was the end, I think, of this page. Sorry. Determine the points of intersection of f of x and g of x when f of x equals 2x plus 1, 2 to the x plus 1, and g of x equals 4 to the 2x minus 3. So when you see determine the points of intersection between two functions, that is a good hint that we're going to be setting them equal to each other. So 2 to the x plus 1 equals 4 to the 2x minus 3. In this case, it would be best for us to get our bases to be common bases. So 2 is already prime, which is nice for us, but 4 can be represented as 2 squared, right? And so we'll get 2x minus 3. This will turn, because of our power to power rule, these will multiply. We'll need to FOIL it. So we'll get 2 to the x plus 1 equals 2 to the 4x minus 6. And now that the bases are the same, we can just cross them out and get rid of them. And then we can solve it algebraically. So we will move this x over and the x over. So we'll get 7 is equal to 3x, which we'll get x is equal to 7/3. To find our y, we're just going to plug it back into one of our functions. It doesn't matter which. So we'll get 2 to the 7/3 plus 1. This will turn into 2 to the 7/3 plus 3 over 3, which would turn it into 2 to the 10/3. And you can just leave it at that. I don't think it matters if you write it out. So 2 to the 10/3. Power. No, sorry. It's just x equals 10/3. My bad. No. Sorry, I'm getting confused. Hold on. So we found our x, and so our x is 10/3. No, our y is 2 to the 10/3, and our x is 7/3. Sorry about that. I got brain fart. I've been doing math all day. Anyway, so our answer would look like 7/3, comma 2 to the 10/3 as a coordinate point. Yes. Next is, and let me just move this over so it's nicer looking. Next we have 15, which is it's telling us that the graphs of f of x and g of x are both graphed on the coordinate system below, and we want to find the solutions to the equations f of x equals g of x, which basically means we're finding the coordinate, the intersection point. So we have a point here, we have 2 points here, and we have, we have 1 point here where they hit. So for A, our answer will be 4, comma, -2. That's where that point is. For B, we'll have 2 answers, and one will be -2, comma, -3, and the other will be 2, comma, 0. And then for the last one, we will have 0, comma, -4. And that is the answer for 15. One sec. Okay. If f of x equals x cubed is the parent function, graph f of x equals negative x plus 4 cubed minus 2. So this follows the transformations that we see in this class pretty frequently, where if it's by the x, it kind of does the opposite of what we think. If it's outside, it moves up or down, and if it's negative, it reflects. So let's graph. So it's negative x plus 4 cubed minus 2. One sec. Negative. I already forgot it. Minus 2. Ah. So the parent graph of this function, oops, let me delete this. The parent graph of this function is x cubed. And we have a point here, here, and here. And then the rest kind of doesn't matter too much for what we want to do. And so it will look something like this. But because we do reflections first. So our new graph would look like this instead, where the y's flip. But also, it's moving to the right by 4, the left by 4, and it's moving down 2. So this would be our new graph, and that is the answer. Let's go back up. 17 is telling us to give the domain and range of the function f of x equals x squared minus 8x plus 2. Put your answer in interval notation. So the domain of quadratic functions, given there are no restrictions, the domain will always be, the domain will always be all real numbers. So, but in interval notation, that's the same as saying negative infinity to positive infinity. However, with range, it depends on whether we are doing this or this. So we need to graph this, or we need to find the vertex somehow. My preferred method of finding the vertex is by completing the square, but there's also the vertex formula, which I believe is just negative b over 2a. Negative b, so negative 8 over 2 times 1, we'll get 8 over 2, which is 4, and that is our x point, I believe. And we would just plug in 4 for x to get the y. But I don't like that way because I always forget if this is actually the formula or not. So I'm going to do it by completing the square. I find it very useful to complete the square because it's you don't need to memorize a quadratic equation if you do that. You can solve it, any quadratic expressions. And also it helps with graphing. So I'm going to do x squared minus 8x plus 2. I rewrite. My first step is to rewrite. I do plus a box and minus a box. My method differs a little bit than Emily, who is our instructor for this semester that I'm mentoring for, her method. The way that she does it, let me do this. So this is my method. She does x squared minus 8x, and she moves the 2 over to the other side of the equation. So she does minus 2, and then plus something, and plus something here. And the thing that goes into our box, or our something, we divide our b term by 2, which gives you negative 4, and then you square that. So negative 4 squared is positive 16. And you just replace your guy there. And then this part, will cross out. And it will become, essentially what we're doing is we're factoring. But the way that we set it up, it will become x minus whatever this was divided by 2. So x minus 4 squared. And then I have the negative 16 plus 2 on this side. And she has the, she just has the x minus 4 squared on this side. And this is negative 14. This is vertex form on my side, but we need to move the 14 over on her side. And to find the vertex, it's usually going to be positive 4 comma negative 14. Now this is not, it's not asking us for the vertex though, it's asking us for the domain and range. Because the coefficient of our x squared is positive, it's going to be looking like this. And it's going to be hitting negative 14. It's going to be at negative 14 as its lowest point. So our lowest point is negative 14. And then it goes all the way to infinity. And infinity usually is a soft parentheses. Hold on. Let me fix this real quick. So this is our answer. Our range is going to be negative infinity, our domain is going to be negative infinity to positive infinity, and our domain is going to be, our range is going to be negative 14, inclusive to infinity. 18 is asking us, if f of x equals 3 of x is the parent function, explain the transformations that would be made to graph f of x to arrive at the graph of f of x equals negative 3 to the x plus 2 minus 3. So we know that we reflect, because there's a negative on the outside, reflect across about the x-axis. Hold on. Let me make my thing a little smaller. That's our up and downs. And then we are also moving to the left by 3 because we have by 2. Because we have a plus 2 in our exponent. And then we're also going down by 3. It follows our other typical transformations. 19 is asking us if the parent function f of x equals log of x is shifted right 2 units and then reflected in the x-axis, what would be the resulting function? We have our f of x equals, it's shifted, it's reflected by the x-axis, so we'll have a negative, and then it's shifted right by 2, so we're going to be minusing 2. That is our resulting function. Pretty simple. 20 is asking us for the inverse function of the set of ordered pairs, or give the reason why the inverse function does not exist. So for this one, you're basically swapping your x and y's, but we do have an issue. An inverse function needs to be 1-to-1, and also function has to be a function first to have an inverse function. So it has to pass both the vertical and the horizontal line test. So the first, we have no repeats of x and y's. We have a 2, 4, 9, 7, 5, a 1, 2, 3, 6, 4. So this does have an inverse because there's no repeats of our y's and there's no repeats of our x's. So the inverse function would be 1, 2. We're just swapping all our x and y's. 2, 4, 3, 9, 6, 7, and 4, 5. This one, we have a problem because we have 2 repeating x's. This actually means that it is not a function. And so you need a function for the inverse. Because I'm scared sometimes, I would still write out the inverse function. But I would say that there's no inverse. Because I feel like the more that you write, the better. Because they can at least see if you know your concepts. But for now, because I'm feeling a little lazy, we're just going to say no inverse function. Because it's not a function. This one, we have no repeating x's, but we do have repeating y's. We've got a 2 and a 2 here for our y's. So there's no inverse. Whoops. But in this case, it is a function. It's just not 1-to-1. So that is 20. 21 is telling us if the domain of a function is a set of values 1, 2, 3, 4, and 5, and the rule is add 1, then multiply by 3, write the set of ordered pairs that represents the values. In this case, we are just going to, we're taking 1, 2, 3, 4, and 5. First, we'll start with 1. We'll add 1, so 1 plus 1 is 2, and then we'll multiply by 3. So 2 times 3 is 6. 2 plus 1 is 3 times 3 is 9. 3 plus 1 is 4 times 3 is 12. 4 plus 1 is 5 times 3 is 15. And 5 plus 1 is 6 times 3 is 18. So that is your answer for 21. 22 says find the x-intercepts if they exist for the function f of x equals 5 times x plus 4 squared minus 15. So to find x-intercepts, we need to set the equation equal to 0. So 0 is equal to 5 times x plus 4 squared minus 15. We want x by itself, so we're going to move 15 over. So 15 is equal to 5 times x plus 4 squared. We're going to divide both sides by 5. We'll get 3 is equal to x plus 4 squared. Then we'll take the square root of both sides. And we'll get plus or minus the square root of 3 is equal to x plus 4. And we'll minus 4 from both sides. So these are your x-intercepts. However, they will want them in a coordinate point. So it would be negative 4 plus the square root of 3, comma 0. And then comma, negative 4 minus the square root of 3, comma 0. And that would be your answer for 22. For 23, it's asking us to determine the 0 which is the x-coordinate of the x-intercept, of the rational function r of x equals x minus 3 over x squared minus 4. So to do this, we're setting the zeros. We need to set our r of x, our y equal to 0. So 0 is equal to x minus 3 over x squared minus 4. This one's kind of trying to trick you with the bottom, because the bottom is really nice and factorable. You get x plus 2 and x minus 2. However, the bottom is not really entirely relevant unless one of the factors is what the top is. So what is happening is if you have a fraction, 0 over anything, aside from 0, we don't allow that. 0 over anything still equals 0, right? If you have 0 parts of a whole, you have 0 parts. So we actually only need to worry about the top, the x minus 3. We're basically multiplying both sides by x plus 2 and x minus 2, but 0 multiplied by anything still equals 0. So if 0 equals x minus 3, we'll add 3 to both sides. We'll get 3 is equal to x. So our 0 is positive 3. We'll just say x equals 0. X equals 3. Now we are moving over to 24, right? Yeah, 24. 24 is telling us that the graph shown below represents a transformation of the parent function f of x equals 1 over x. Write the equation of the transform function in our nice rational transformation form. I'm sure it has a name, I just don't remember what it is. So our original, we start here. So it looks like we moved 1, 2, 1, 2. It looks like we moved down 2 over 2, give or take. Well, it's like 0.5. It's kind of weird. You have to do like negative 2.5. So it'd be 1 over x plus 2.5. And then we're going down by 2, give or take. It's like, there's like a tiny itty bitty, I think there's a gap. Maybe I'm going insane. No, I'm going insane. It's not 2.5. Sorry. I'm being thrown off by the actual grid of my program. I'll turn it off. Sorry. So it's down 2 over 2. So it's plus 2. Sorry. That was silly. That's our function. And we would want it to be f of x or y. For 25, it wants us to determine the range of the exponential function, f of x equals 4 to the x minus 3. Now, with exponential functions, we know that with the parent graph, it never crosses 0. But because we're moving down by 3, our horizontal asymptote also moves down by 3. So it will never cross 3, negative 3, but it will hit everything else. So negative 3, exclusive, because it's never hitting it, to positive infinity is our range. 26 says, determine any maximum or minimum, global or local, function values of the function graphed below. So we have a point here, we have a point here, we have a point here, but because this one goes down for forever, we don't really need to write that out. So the global, and I don't know if you'll need to know, like identify which ones are global or local, but the global is this point because it stops, it doesn't keep going up. So we have a point of, I'm just gonna say it's 4, 4 comma 4. We also have a point at 2 comma negative 3, and we also have a point at negative 1 comma 1. So those are your minimum and maximum values. It's basically any turning points, as well as any highest or lowest points. Next, we have if f of x equals negative 3 of x, and g of x equals x squared plus 4x minus 2, find f of g of x. This is the same as writing a fog, basically. So we'll do negative 3 times x squared plus 4x minus 2 plus 5. We'll distribute, so we'll get, well, I'm actually going to factor the inside first because I think that makes life a little bit easier. If it is factorable, I actually don't think it's factorable, so scratch that. So it'd be negative 3x squared plus, minus 12x plus 6 plus 5. So 6 plus 5 is 11. I'm going to do the AC method. Negative 3 times 11 is negative 33. It actually might not want us to factor, but it might. Let's see. If this factors nicely, that's great. It probably, I don't think it'll factor nicely, though. Yeah, it won't factor nicely. So we'll just leave it at this. Negative, because it's not asking us to solve for, like, x or anything like that. So that would be our answer for 27. And let me cut and paste that. 28 is asking us if f of x equals e to the x minus 4 and g of x equals e to the 2x plus 9, determine the product. So we are multiplying these guys together. So e to the x minus 4 equals e to the 2x. No, not equals. Sorry, we're not finding intersection points. We're multiplying. E to the 2x plus 9. Because of our exponent rules, if we have the same base and they're multiplying, the exponents will add together. So we'll have x plus 2x, so 3x, e to the 3x. Negative 4 plus 9 is positive 5. So our answer will be e to the 3x plus 5. 29 is telling us, let me cut and paste this. Oh, whoops. 29 says, if f of x equals 5x cubed minus 125x, write f of x in a completely factored form. So my first instinct when I see this is I see a 25 and a minus. So I think, oh, it's a difference of cubes because there's a cube here also. But actually, whenever we are doing things like this, we actually need to take out a GCF first. And this, they both have a GCF of 5x. So I'm going to take a 5x out, which gives me x squared minus 25, which is still nice because this is the difference of squares. So we'll get 5x times x plus 5 and x minus 5. And that will be our completely factor form. 5x times x plus 5, x minus 5. I have a video on the difference of squares in my channel, but there's also lots of resources. If you aren't sure on how to do that, I would recommend checking those out. But this would be our answer for 29. Okay, it looks to me like we are going to need another white canvas because there's lots of busy things happening. 30 is telling us, oops, hold on, let me change my color back to how it was before. No, I'm actually going to change to a nice blue. That's what I'm feeling. So we're about halfway through. I think we're a little more than halfway through. Whew, take a deep breath. That's a lot of math. Anyway, 30 is saying if f of x equals x to the 4th power plus 2x to the 3rd power minus 8x minus 16, we want to write it in completely factored form. When you have 4 terms like this, it's a good indicator that we're probably going to be factoring by grouping. So we just split these apart and look for GCFs. And our goal is to get the insides to be the same. So I'm going to take out an x squared, x cubed here, which would leave me with x plus 2. And I'm going to take out a negative 8 from here, which would leave me with an x plus 2. Hooray! We have 2x plus 2s, so we're going to take those out by factoring them out. And we'll be left with an x plus 2 and the leftovers, which is an x cubed minus 8. Now, we think we're done. That was a lot of work, but actually x cubed minus 8 is a difference of cubes. The difference of cubes formula. Let's go down here because it's something you probably want to know. So there's both the sum and difference of cubes. Let's talk about the sum of cubes and the difference. So for the sum of cubes, we'll have an a cubed plus b cubed, and that's the same as a plus b, a squared minus ab plus b squared. In both our sum of cubes and difference of cubes, there's going to be one negative, but in the sum of cubes, it happens here, and in the difference of cubes, it happens in the beginning. So a minus b, so we have a cubed minus b cubed. That's the same as writing a minus b times a squared plus ab plus b squared. So it's just a matter of where the negative goes. Now, knowing that, let's come back up here. But I want to copy paste this because this is my work layer. Whew. Okay, so now we can rewrite this as x plus 2 and then x minus 2, x squared plus 2x plus 4, because that's 2 squared. So this is our completely factored form. You won't be able to go further with this. It seems tempting, but you won't be able to ever. So you can rest easy not going further with that. 31 says find f of 27 for the function f of x equals 4 times log base 3 x plus 2. So there are a few different ways that you could go about this. I have a 4 times log base 3 x plus 2. Sorry, the x is on the outside. We need to replace the x with a 27. The way that I went about this is I did 4 times log base 3, and I know 27 is 3 cubed. And I know that because we have a 3 and a 3, these will cross out, leaving us with a 4 times 3, and then plus 2, which will give us 14. However, I know that a lot of people kind of balk when there's like a log base 3 to 3. So an alternate way of going about this would be doing 4 times, we could either plug this into our calculator by doing log 27 over log 3. This is our change of base formula where you just kind of cross through, giving you a log on top, a log 27 on top, and a log 3 on the bottom. And you can plug it into your calculator like this. Be so careful with your parentheses though, because a lot of people forget closing parentheses when their calculator gives them that extra thing, and then plus 2. And then they just plug it into their calculator. That's totally fine too. Yeah, so that is 31. Whew. Next we have 32, which is determine the domain of the rational function r of x equals x plus 5 all over x squared plus 8x plus 12. And we want to write the domain in interval notation. So we have x plus 5 over x squared plus 8x plus 12. Now, I know that a lot of you are familiar with factoring by grouping when, well, actually, it's not applicable. We need to, the domain is basically restrictions. So we need to find what will make the bottom 0, because that's a problem. We can't be dividing by 0. So we need to factor this to find our zeros. X times 12, like 1 times 12 is 12. We have 2 and 6, which seems like our lucky winners. So we'll get x plus 5 over x plus 2, x plus 6. Those are our factors. And so our problems, what x cannot equal, is -2 and -6. So our domain, let's move this down a bit. Our domain is going to be, oops, sorry, hold on. Let me pause. Our domain is going to be negative infinity to -2, union -2 to, oh, sorry, that should be -6. Because we do smallest to largest, and -6 is smaller than -2. Union -2 to positive infinity, and that would be our domain of our function. 33 says find all the zeros of the exponential function of f of x equals 4 to the x plus 5 and then -16. That means we set f of x equal to 0. So 0 is equal to 4 to the x plus 5 minus 16. I'm going to add 16 to both sides, so I'll get 16 equals 4 to the x plus 5. 16 can be expressed as 4 squared. So we'll do 4 squared equals 4 to the x plus 5. Now all of our bases are the same, so we can cross them out. So we get 2 is equal to x plus 5. So we'll get -3 is equal to x. And that is our 0. So we'll get x is equal to -3. Woohoo! The next problem is 34, which says determine the x-intercepts of the logarithmic function f of x equals log base 2, x plus 4 minus 3. So the x-intercepts, that's when y equals 0. So we'll do 0 is equal to log base 2, x plus 4 minus 3. We're going to add 3 to both sides, so we'll get 3 is equal to log base 2, x plus 4. Now we'll change it into exponential form, so base 2 to the 3rd power. That's the same as writing 8. 8 is equal to x plus 4. Well, minus 4, we'll get x is equal to 4. Yeah, x is equal to 4. but it wants the x-intercept, so we'll say 4 comma 0. Whoops. 35 is asking us to find the linear function in slope-intercept form whose graph passes through the points 2, 5, and 5, minus 1. 5, negative 1. So we are going to use our slope formula, which is m is equal to y1 minus y2, y over 2, over x1 minus x over 2. Now, I've always hated this because it feels so stuffy and mathy, but basically it's saying if you had these plotted, we would have one at 2, 5, so 2, 5, and we would have one at 5, negative 1. And we're saying, what's our rise over run? So we go 1, 2, 3. We go over 3, and we go 1, 2, 3, 4, 5, 6, up 6. And we would find, which would mean our slope, but it's a downward slope. So we would have a slope of negative 2. This is the exact same as plugging in our points here. So we have a 5 minus negative 1 over a 2 minus 5, which is the same as saying 6 over negative 3, which is the same as saying negative 2. That's great for us. We have our m, but we still need our b. So we're going to take our x and our y, because we're given an x, we're given 2 x's and 2 y's, but we need to pick a pair. And we'll say 5 is equal to negative 2 times 2 plus b. This is going off of our y equals mx plus b. So we get 5 is equal to negative 4 plus b, which is going to give us 9 is equal to b, which means that our slope-intercept form would be y is equal to negative 2x plus 9. And that is the answer for 35. 36 says construct a linear function with the slope m equals 1/2 that passes through the point negative 3, 8. So our linear function, it's so nice for us because it gives us an actual slope. So we don't have to use our slope formula, but we still do need to replace our points. So x is equal to 1/2 times 8, negative 3 plus b. So we'll get 8 equals negative 3/2 plus b. We'll add 3/2, so we'll get 8 plus 3/2 equals b. 8 is the same as 16/2 plus 3/2, so we'll get 19/2 for our y-intercept. So our equation will be y is equal to 1/2 x, and then plus 19 over 2. That one's kind of gross. I don't like when we have fractions, but that's okay. Next, we are finding the linear, it's 37, and we are finding the linear function whose graph passes through the points negative 4, and is parallel to the graph of the function g of x equals negative 3/4 x minus 2. Because it's parallel, we know our slope is the same. So we will have negative 3/4, and we're just going to do the same thing that we did last time, where we're plugging in negative 4 for our y and negative 4 for our x, and then plus b. The 4's will cross out, and the negatives will cross out. So you'll get negative 4 is equal to 3, and then you'll get plus b, sorry. You'll get negative 7 is equal to b. Whew. So our equation will be y is equal to negative 3/4 x minus 7. Yes. Yeah. 38 says construct a linear function whose graph is parallel. Again, we're talking about parallel to the graph of the function g of x equals 3x minus 4, and passes through the point 0 over 0, 3/5. So the parallel, this is actually super nice for us because it's already giving our b and it's already giving our m. So our new function will just be y is equal to 3x plus 3/5. That's 38. It's pretty simple. The point 1, sits on the graph of 1 over x, and we are transforming it to a new function. Where will our point move? So we have x plus 3, which means we're going left 3, and then plus 4, which means we're going up 4. So we're going to add 4 to our y, so we'll have well, we're going to minus 3 from our x, so we'll get negative 2. And then we're going to add 4 to our y, so we'll get 5. Negative 2, 5 is our answer for this problem. Excuse me. Alright, so 40 is asking us to determine the function obtained from transforming the parent function f of x equals log 11x by shifting the parent function up 2 units left, and then stretching it by a factor of 4, and then shifting it up by 3. Our new function, since we're stretching it by 4, we'll times it by 4, log base 11. We're shifting it 2 units left, so x plus 2. And then we're shifting it up by 3, so plus 3. This is our new function. It's following the typical transformation rules. 41 is, hold on, sorry. 41 says if f of x equals x squared is the parent function, graph the function f of x equals negative x plus 2 squared minus 3. So, yeah, negative x plus 2 squared minus 3. Negative x plus 2 squared. I already forgot it. Minus 3. So, our parent function is, excuse me, it will look something like this. But because we are reflecting it, it will look like this instead. And then we're going to be moving it to the left by 2. The left by 2. And then we're going to be moving it down 3. So this is our new function. Yeah. That is the answer for 41. 42 says the parent function, f of x equals 2 to the x power, is just be shifted 2 units left, and then reflected across the x-axis, and finally shifted up 1 unit, we're going to graph it. So our new function, so it's shifted 2 to the left, sorry, we have a base of 2, and then it's plus 2. And it's reflected across the x-axis, so it's negative. And then it's added 1. So our parent graph looks something like this. Whoops. But it's being reflected, so we're gonna do this. Whoops, it's still a little squished. There we go. And then it's also going to be moving to the left by 2, and it's going to be moving up 1. So this is our new graph. Whew, my voice is starting to go. That's all right. So that's the answer for 42. The answer for 43 says, 43 is asking us, find the inverse function of f of x equals negative 2x minus 4. We have to change our f of x to y's. So we'll get x is equal to negative 2y minus 4. Now we'll add 4 to both sides. X plus 4 equals negative 2y. We'll divide both sides by negative 2. And we'll get negative 1/2 x minus 2. So that is our inverse function. And the notation for that would be f of negative 1 of x is equal to negative 1/2 x minus 2. And that is your answer for 43. You just swap x and y's. 44 says graph the function x squared plus 2 on the restricted domain 0, infinity on a rectangular coordinate system. Then graph f of negative 1 of x on the same system. So the inverse. The reason, sometimes people are scared by the restricted domain part, but the reason why they give this is so that it's 1-to-1. So x squared plus 2, we'll move over here. Our original function looks something like this. But we moved it up 2. And so this is the new function, but we also want to graph the inverse. So we're going to find our points. We have a 0, 2. We have a 1 comma 3, and we have a 2 comma 6. Now to mention the domain stuff, we have a restricted domain of 0 to infinity, so we're including 0, but we're not including anything behind 0. So that will make our inverse one-to-one function. So now we're just graphing the opposite points. And our inverse graph will look like this, and our transformed graph will look like the blue one. And I think I want to stick with red for my future stuff. So let's go back to where we were. We were on 44. That was the answer to 44. 45 says find the inverse function of f of x equals 3 times 5 to the x power minus 2. So we need to swap our x and y. So we'll have x is equal to 3 times 5 to the negative y minus 2. We'll add 2 to both sides. We'll divide both sides by 3. I don't know why I said negative y. It's not negative, it's just positive. And then now we need a logarithmic form. We have a log base 5 to x plus 2 over 3 equals y. And so our inverse function will be f to the negative 1 of x is equal to log base 5 to the x plus 2 over 3 equals, well, we did that. We just moved it to the front. That is your answer for 45. You just need to know your logarithmic functions. 46 says determine the inverse function of f of x equals 3 times x squared plus 12x minus 5x, and then it gives us another restriction. We're saying everything bigger than negative 2. So we need to first factor. 3 times negative 5 is negative 15. Negative 15, what multiplies up to negative 15? That also adds up to 12. Well, we have a 3 and a 5. We have a 1 and a 15. We might not have anything nice for this. I think we ought to. Oh, sorry. We're doing the inverse. We aren't factoring. So we need to actually complete the square. So I'm actually gonna complete the square first before I do the inverse, just because it's gonna be a little bit nicer in my head first. So I'm taking a 3 out. X squared plus 4x. Minus 5. I like doing it my way. I think it's fun. They're like little glasses for little nerds. And then divide by 2. 2 squared is 4. You get 3 times x plus 2 squared plus 4, minus 4 I mean. Minus 5. To take this out, we need to multiply by 12. So we get 3 times x plus 2 squared. Minus 12 minus 5 is negative 17. Yeah. And then now we can swap our x and y. So we get 3 times y plus 2 squared minus 17 equals x. We need to solve for y, so I'm going to add 17. So I have 3 times y plus 2 squared equals x plus 17. Divide both sides by 3, so you get y plus 2 squared equals x plus 17 over 3. We need to square root both sides, so you get y plus 2 is equal to this plus or minus. Now, here's where the restriction gets important. Because it's everything bigger than negative 2, we're actually going to be dealing with the plus side. So it'll be plus x plus 17 over 3, the square root of that, and we'll minus 2, which will give us f of negative 1 of x is equal to negative 2 plus the square root of x plus 17 divided by 3. And that is the answer for 46. 47 says determine the points of intersection of the graphs of the two polynomial functions f of x equals x squared minus 5 and g of x equals 4x. When you hear the intersection point, you set them equal to each other. I'm going to move the 4x over, so we'll get x squared minus 4x minus 5. We'll factor, we'll do negative 5, 1 and 5, probably 1 and negative 5. So we'll get x plus 1 and x minus 5. So it looks like we'll have an x of negative 1 and we'll have an x of positive 5. But now we need to find the y, so we'll just plug these into one of the functions. I'm going to choose this one because it looks simpler. Negative 1 times 4 is positive 4, and 5 times 4 is 20. So our intersection points are going to be -1, 4, and also 5, 20, and that is the answer for 47. Next, we have 48, which says determine the points of intersection on the graph of the functions f of x equals 4x plus 1, and g of x equals x minus 2. So we'll set them equal to each other. 4 times x plus 1 equals x minus 2. We're going to distribute the 4, so we'll get 4x plus 4 equals x minus 2. I'm going to move the x over, so we'll get 3x, and I'm going to move the 4 over, so we'll get -6. X equals -2, because -6 divided by 3 is -2. And now I'm going to plug in the -2 to my original functions. I'm going to choose this one since it looks simpler. So -2 minus 2 is -4. So we'll have -2, -4. And that is the point of intersection on the graph. So -2, -4. Next, we have 49, which says find the points of intersection on the graphs of two linear functions, which is 3 of x minus 9 and g of x equals 4x plus 11. And so we will have, we'll set them equal to each other. 3x minus 9 equals 4x plus 11. I'm going to minus the 3 over, so we'll have -9 is equal to x. I'm going to then minus the 11 over, so I'll get -20 is equal to x. So it looks like -20 is our point. I'm going to plug it into probably the 3x one. So 3 times -20 minus 9 gives me -60 minus 9, which gives me -69. So I will get -20, -69 for the answer for 49. Nice. Next, we have 50, which says determine the solutions, real or complex, of the equation x squared minus 5x equals 3x squared plus 7. So we will I'm going to minus the x squared over to the other side. Well, I'm going to set it equal to 0. So I'm going to have 2x squared because 3x squared minus x squared equals 2x squared. 7, we'll just have a plus 5x because there's no like terms to add to, and then plus 7 equals 0, and I moved it to this side just because it works a little better in my brain this way. 2 times 7 is 14. What multiplies up to 14? That gives us 5. Well, we have 2 and 7 only. However, this is causing problems because 2 and 7 do not add up to 5. Maybe if one was negative. Hold on. I think that this one has a gross answer. I don't think this one is nice. So what we'll need to actually do is either completing the square or doing the quadratic formula. I like doing the completing the square, but actually in this one I'm going to do quadratic formula because I don't want to deal with any fractions here. So I'm going to say negative b, which is -5, plus or minus the square root of b squared, so 5 squared, minus 4 times a, which is 2, times c, which is 7, all over 2a, so 2 times 2. So I'll get -5 plus or minus 25 minus 56. So we're going to have an I in this one, which is always fun to deal with. We'll have -5 plus or minus -31, the square root of -31, but I'm going to take out an I so we can have a positive in there, and then it's all over 4. So these are our solutions. Kind of yucky, but it is what it is. So we have -5 plus or minus I times the square root of 31 all over 4. So yuck, but it's okay. We are adults and we live with it. Anyway, next. We're almost done. There's 6 more. Except for 51 is one of the hardest. I think it's the hardest on the review. So let's go through this one together. 51 says determine the, it says solve the equation 2 times e to the 3x plus 1 equals 6 times e to the x minus 4, and we want to leave it using the natural logarithm. So this one is tricky. First step, so our ultimate goal is to get x by itself, but there's going to be a lot of winding and twisting trails. So we're going to divide both sides by 2 first. We'll get e to the 3x plus 1 equals 3 times e to the x minus 4. Now here we need to convert from exponential form to logarithmic form. My preferred way of doing this is doing ln to both sides. We're allowed to do this because whatever you do to one side, you have to do to the other. It's not changing the value of the equation, it's just changing how it looks. This would cross out, giving you 3x plus 1 equals ln 3 times e to the x minus 4. However, we could also say, we have a base of e, so it'll be ln, and then our answer is 3 times e to the x minus 4, and then our exponent would be 3x plus 1. But a lot of students I find get kind of confused here because we have a e on both sides, but one has a 3. So you have to be really careful if you're going to go this route. Either way, it gets you the same thing here. Now we need to use our logarithm rules to separate some things. So 3x plus 1 is just coming along for the ride with us. We know with our logarithms, so if they're multiplying together, we can separate them by addition. So ln 3 plus ln e to the x minus 4. Here, you could either catapult this. Well, you have to catapult it either way. No. Because ln e equals 1. You can just cross that out. Or you could catapult it, but eventually you'll come to the conclusion that ln e equals 1. So you'll get 3x plus 1 equals ln 3 plus x minus 4. We'll add 4 to both sides, so we'll get we want to get all our x's on one side and all of our non-x's on the other sides. So I'm going to actually minus x from both sides, so we'll get 3x, and I'm going to minus 1 from both sides, minus x, so it turns into 2x equals ln 3, and this cannot be added or subtracted with our 4, but minus 1, so we get minus 5 instead. Now we just divide both sides by 2. We'll get x is equal to ln 3 minus 5 over 2. That would be your answer for this equation. It's gross. That's as far as we're going to go, though, with it. And I don't know if you'll see something like that, but I can't say for certain. So ln 3 minus 5 over 2 is your answer. For this one. Woo, that was a long one. It's just tricky. 52 says if the function f of x equals 1 over x is translated by shifting it 4 units right and 3 units down to form a new function, we need to find its inverse in standard form. So we have, first we're shifting it 4 units right, so x minus 4, and then minus 3. That's our new function, g of x. We need to find its inverse, so we'll just swap the x and y's. So we'll have x is equal to 1 over y minus 4 minus 3. We need to add 3 to both sides, so x plus 3 equals 1 over y minus 4. We'll multiply both sides by y minus 4 to get it out of the denominator because we can't do anything with it down there. So it'd be y minus 4 times x plus 3 equals 1. We'll FOIL, so we'll get xy plus 3y minus 4x minus 12 equals 1. We'll move all of our everything that has no y's over to the other side. And now we're going to factor out a y from both our sides, from this side, so x plus 3. We'll divide both sides by x plus 3. This is also a really tricky one. So we will have f of negative 1 of x is equal to 4x plus 13 all over x plus 3. And that is the answer for 52. For 53, we are saying if f of x and g of x represent one-to-one functions, we have a restricted domain for the second one, and both functions are vertically shifted up 2 units and horizontally left by 2 to form new functions. Where would the point of intersection on the new functions be? This one, we I personally, so you could make the changes to the functions now, but I would actually prefer to find the point, the intersection point first, and then make the changes to that specific point. So I'm just going to do this, set them equal to each other because we're finding the intersection point. We're going to move x squared, we're going to move the other two over, so it'll be x squared minus 2x plus 1. This is 2 and 2, 1 and 1. We'll have it negative 1 and negative 1. So we'll have x minus 1 times x minus 1. So we will have x equals 1 twice. So we have two solutions. That's why it gives a restricted domain, because it's kind of weird when you have two of the same things. Anyway, we'll plug this back into our function. I'm going to do this one because it's easier to me in my head, but it really doesn't matter. You'll get 1 squared is 1, so you'll get your point, your intersection point is 1, 1. But we do have the shifts, so we go up by 2, so 1 plus 2 is 3. And we go left by 2, so 1 minus 2 is negative 1. So our point is negative 1, comma 3. We're so close. 3 more. So 54 says f of x and g of x are both graphed on the same graph below. At what point will the inverse of f and the inverse of g intersect? So a lot of people think that this is a good time to do reflections and stuff, but I actually wouldn't recommend that. We just need to find the intersection point, which is 0, 1. So the inverse of that is just going to be 1, 0. So that's your answer. This one's super simple. They threw in a freebie at the end. Next, we have 55, which says construct a linear function that has the same y-intercept of the logarithm function that it gives, and it has an average rate of change of 4. So we know right off the bat we're going to have something like y equals 4x plus b. We need to find the y-intercept of our logarithm function first, though, and we set x equal to 0 because we're finding the y-intercept. So log 2, 0 plus 2 is 2, minus 3. Log 2, that crosses out and turns into 1. 1 minus 3 is equal to negative 2. So our y-intercept is negative 2, giving us the answer of 4x minus 2. Finally, our last one. It's been an hour and a half. Determine the quadratic function graphed below. So we have 2. The parent function looks something like this, but it looks like we moved down by 4 and over by negative 1. So we'll have f of x is equal to, there's no stretches, so we'll just be x plus 1 squared minus 4. And this one is similar, f of x, but it's like half. I don't like when they throw that, and I don't think you'll see something like that on the exam, but don't quote me there because you never know. But we're basically moving to the right by 0.5. And it's slightly below 2, but I'm just going to say it's minus 2. And I'm going to rewrite this to 0.5 because that looked like a mistake. So these are your answers for this, for A and B. Now, we made it through. I guess zooming back into things to know. We didn't do very much log separation stuff, but it might be good to review. Here's another good thing for you to know of log. If you have a log with the same base of like x times y, that's the same as saying log with the base x plus log base y. If you have a log with the base x over, like divided by something, that's the same as saying log base x minus log with the same base y. If you have something like log base b to the x to the y power, that's the same as saying you catapult it. So y times log base b to the x. I like to imagine that if it's on the bottom, it has a negative, and if it's on the top, it has a positive. Because sometimes students get confused if there's like a y times something down here, and they do like plus whatever, like log base b to the z. But that would mean that it was on the top. So I try to think of it less about what's multiplying and what's dividing, and more like, is it on the top or the bottom, and does it get a negative or a positive, based on that. You probably should also know the difference of squared. Which basically says if you have an a squared minus, and the minus is crucial, minus a b squared, that's the same as saying a minus b and a plus b with factoring. You should probably, let me think. I think those are like the more crucial ones. I'm sure I'm missing something, but yeah. That was the final exam review for the Math 1015. If you have any questions, feel free to ask me. Yeah, I will see you all later.